Hi everyone. So in the last video, we started to talk about how you can find the area between two curves. And so in this video, we're going to continue to talk about the same topic, but we're going to look at some examples that are a little bit trickier for various reasons. So I just want to remind you first what was kind of the general method for finding area between curves from last time. So basically what we said last time is the area bounded by f of x and g of x, where f of x is the upper function. So f of x is greater than or equal to g of x. And the equal sign is there because they might intersect, right? Between x is equal to a and x is equal to b is equal to the integral from a to b of f of x minus g of x dx. So we talked about where that comes from in the last video. Basically, the idea is that if you were to split this up into two integrals, the first integral would be finding the area below the top function, and then the second integral would then subtract out the area under the bottom function. And if the bottom function is negative, then subtracting the negative will actually add that area in. So regardless of whether the functions are positive or negative, it always works out as long as you do top function minus bottom function. So there's one kind of twist, which is that sometimes the function that's on the top and the functions that's on the bottom, sometimes they switch. So sometimes the functions basically cross each other, right? So it's not kind of consistent which one is on the top and which one's on the bottom. And so in that case, what we need to do is basically split the interval that we're looking at into multiple integrals. And so that's what we'll do in a second. So in that case, the area will need to be calculated by two different, or maybe even three different integrals. So basically, the idea is that in order to get this to work, you always have to do top function minus bottom function. And so if that's switching, you're going to have to do a different integral for each different change of what's on the top and what's on the bottom. So let's look at an example. So let's say we wanted to find the area bounded by y is equal to sine of x, y is equal to cosine of x is equal to 0, and x is equal to pi. So let's start by graphing our function. So sine of x is going to go up and hit its maximum at pi over 2 and then go back down. Oops, I didn't do the best job on that. Let me redo that. Then go down like this and then come back up. And then cosine is going to start with a y-intercept of 1. It's going to go down to its minimum value at pi and then come back up. So it's going to look like this. And it really is helpful to draw your pictures accurately on these problems because you need to figure out where the two graphs intersect and also be able to tell what's on the top and what's on the bottom. Okay, so let's start by shading in the area that we're actually talking about here. So actually there's two more things that we have to add to this picture. So this is the graph of y is equal to sine of x. This is the graph of y is equal to cosine of x, but then we have two other graphs that we need to put in. And so one of them is x is equal to 0. So that's going to be this vertical line. But then we also have x is equal to pi. So what area are we looking at? because there's no, specification, like if there was an extra bound of like x is equal to pi over 4, then that might restrict which portion we're looking at. But we're actually looking at this entire portion. So here as well as here, because that's all the part of the graph that is in between all of the different graphs that are provided or equations that are provided. So notice that at the first part of the graph, from 0 to pi over 4, cosine is on the top. But then from pi over 4 to pi, it switches and then sine is on the top. So we're going to have one integral that goes from 0 to pi over 4 and another integral that goes from pi over 4 to pi. And by the way, so like I said, if you draw your pictures really accurately, then that will help you figure out where intersection points happen. If we had not drawn this so accurately, how would you know, exactly what point this was? Well, if you set sine of x equal to cosine of x and solve that, you're basically looking for, what's the angle where sine and cosine agree. And if you think about the unit circle, the angle between 0 and pi, where sine and cosine have the same value, would be pi over 4, right? Like a 45-degree angle, sine and cosine are going to have the same value. So that's why those two graphs intersect at pi over 4. Okay, so let's split this into our two integrals. So I'm going to write this down from x is equal to 0 to x is equal to pi over 4. The function cosine, so y is equal to cosine of x, is on top. And so that part is going to give us the integral from 0 to pi over 4 of cosine of x minus sine of x dx. So let's start by calculating that integral, and then after that we will do the next portion. So what is that area going to be? Well, that's going to, or what is that antiderivative going to be? So the antiderivative of cosine is just sine. And then the antiderivative of negative sine is cosine, right? Because the derivative of cosine is negative sine. So because we have minus sine of x, that's just going to translate to having an antiderivative of positive cosine of x. And so we're going to evaluate that at pi over 4 and at 0. So sine of pi over 4, actually I'll just write it all out. So we have sine of pi over 4 plus cosine of pi over 4 minus, sorry, sometimes my touch screen just like does not want to move. There we go. Minus sine of 0 plus cosine of 0. And so that's going to give us, so sine of pi over 4 is square root of 2 over 2. And then cosine, as we already discussed, sine and cosine of pi over 4 are the same. And then sine of 0 is 0, and cosine of 0 is 1. So we're subtracting 1. So altogether, this is going to give us, so square root of 2 over 2 plus another square root of 2 over 2 altogether is going to give us square root of 2 minus 1. So basically what we just found here is this area here. So maybe I'll use some color coding here. Okay, so now let's find the next part. So the next part is going to be this part here. So for this part of the graph, so now we're going from x is equal to pi over 4 to x is equal to pi. Sorry, pi. Y is equal to now sine of x is on the top. And so for this part, we're going to need to take the integral from pi over 4 to pi of now sine of x minus cosine of x dx. So now our antiderivative, so the antiderivative of sine of x is negative cosine of x. And then the antiderivative of negative cosine of x is negative sine of x. And we're going to evaluate that expression at pi and pi over 4. Okay, so that's going to give us negative cosine of pi minus sine of pi minus negative cosine of pi over 4 minus sine of pi over 4. So cosine of pi is -1, but we have negative cosine of pi, so that's going to become +1. So -1. And then sine of pi is 0. And then we have plus cosine of pi over 4, which we mentioned earlier is square root of 2 over 2. And then we have plus sine of pi over 4, which is also square root of 2 over 2. And so that simplifies all together to 1 plus square root of 2. And so, putting these together to give us our total area, we're going to now take, so we had, for the first part, we had square root of 2 minus 1. Maybe I'll color code this. So we had square root of 2 minus 1 for our first part, and then we had square root of 2 plus 1 for the second part. And so altogether, this is going to give us, so the 1's cancel out, and we're just left with 2 root 2. So that is the total area that we were looking for. One thing, this is kind of off topic, but I just thought of that I keep forgetting to mention. So a lot of these videos keep coming out a little bit longer than I expect them to. And I think a big part of the reason is because, I think I'm going into a lot more detail with my computations in these videos. And so I just wanted to, maybe this is obvious, but, I think the best way for you to follow along in these videos is to kind of pause it and try to do whatever it is that we're doing yourself. So, once we get to the integral, pause the video, do the integral yourself. And that way you can then fast forward through my computations and see whether it matches up with what you did. Or, if you get to a point where you're like, I'm pretty confident I could compute that myself, you can feel free to fast forward through computations. I've basically debated, like, would it be better for me to make my videos shorter by, saying, okay, well, here's the integral and here's the answer, you can compute it yourself. And I figured, I might as well include all the details so that if you do want to watch them, you can, but definitely feel free to fast forward through them if you feel like this video, these videos are just too long and you don't really need to see all of the detail of like adding up fractions and stuff like that. So just kind of a quick thing I just wanted to mention. Okay, so this is one kind of situation that can arise. So you can have a situation like this where basically you only have two functions, but the one that is on the top and the one that's on the bottom switches. But now we're going to look at an example where we actually have three different functions. And it will kind of play out similarly to the last example we did because we'll see that we have to split it up into two different integrals. So in this example, I want to find the area of the region bounded by. So in this case, we have y is equal to x squared plus 1, y is equal to negative 2x plus 4, and y is equal to negative 1/2 x plus 1. Okay, so let's start graphing these. So we have x squared plus 1, so that's going to be a parabola. Start drawing the shape. So here we have y is equal to x squared plus 1. Then we have negative 2x plus 4, which I guess I didn't quite leave enough space here, but let me say maybe 4 is there. So negative 2x plus 4, I think it's actually probably a little lower. It's probably more like here. I just barely didn't make it enough. So negative 2x plus 4 would go through this point, right? Because of the slope being 2. And so it would look like this. And then our last graph is negative 1/2 x plus 1. So that would have a y-intercept of 1 and a slope of negative 1/2. So that means that it would go like this. Oops. And it would continue to go this way as well. So this is y is equal to negative 1/2 x plus 1. So again, if you're careful with your with the way you're doing it, you should be able to see where they intersect. But if not, you could always set the equations equal to each other, and that would give you the same answers. So this is the area we're looking at. So in this case, we basically need to, again, switch this or split this into two different integrals. And the reason for that is because, so the bottom function is always y is equal to negative x squared plus 1, right? This is always our bottom of our, going from left to right, this is always on the bottom. However, as we move from left to right, so, and again, like in the last video, I mentioned this idea of kind of like drawing these little vertical lines to kind of just check in with, okay, what's on the top, what's on the bottom. So if I draw this vertical line here and I'm kind of scanning from left to right, the parabola is on the top and this function's on the bottom, right? But as soon as I hit x is equal to 1, all of a sudden it switches. So if I draw a line here, well, now y is equal to negative 2x plus 4 is on the top, and y is equal to negative 1/2 x plus 1 is on the bottom. So at x is equal to 1 is where it switches from what's on the top and what's on the bottom. And I've found that students often have a little trouble, again, with like figuring out what's on the top, what's on the bottom, especially when you have multiple, more than two functions going on. So I really, really recommend this method of like drawing a vertical line and then just literally asking yourself what's at the top of the line and what's at the bottom of the line. And that will tell you the top and bottom function. Okay, so we're going to split this into two parts. So the first part we're going to do is going to be this part. So to find this area. So for the first part, from x is equal to 0 to x is equal to 1, y is equal to x squared plus 1 is on top. And as we mentioned before, that line is on the bottom. Y is equal to negative 1/2 x plus 1. And so that means that to find that area, we'll do the integral from 0 to 1 of, x squared plus 1. And then from that, we want to subtract negative 1/2 x plus 1. Okay, so let's simplify this a little bit before we go in and evaluate it. And actually, I'll go over here. So we have the integral from 0 to 1 of x squared plus x plus 1/2 x minus 1. And that simplifies even more to become now just the integral of x squared plus 1/2 x, because those ones cancel out with each other. Okay, so now we can find the antiderivative. So our antiderivative is going to be x cubed over 3. And then the next part we have, so the antiderivative of just x would be x squared over 2, right? But then we also have this 1/2. And so that's going to give us actually x squared over 4, right? Because we have 1/2 times 1/2. And then we're going to evaluate that at 1 and at 0. So when we plug in 1, we get 1 over 3 plus 1 over 4. And then when we plug in 0, we just get 0 on both parts. And so we can make a common denominator here of 12. So that will give us 4 over 12 plus 3 over 12. And that gives us a total of 7 over 12. So that's the first part of our area. But then we also have this second part. So we want to also find this area here. And so for that part, so that's from 1 to 2, now the other linear function is on the top. So negative 2x plus 4 is on top. So from x is equal to 1 to x is equal to 2, y is equal to negative 2x plus 4 is on top. And so that means that we want to do the integral from 1 to 2 of negative 2x plus 4 minus negative 1/2 x plus 1. And so that is going to simplify a little bit. So we have negative 2x plus 4 plus 1/2 x minus 1. So we can simplify this integrand a little bit, right? And so now we have the integral from 1 to 2, and so negative 2x plus 1/2 x is going to give us negative 3/2 x. And then we have 4 minus 1 is 3. And so now we can take antiderivative. So the antiderivative of x is x squared over 2, and then we multiply that with negative 3/2 for a total of negative 3/4 x squared. And then we have plus 3x. And we're evaluating this at 2 and at 1. So when we plug in 2, we're going to get negative 3/4 times 4 plus 3 times 2 is 6. And then we're going to subtract from that negative 3/4 times 1 plus 3 times 1 is 3. So altogether, we end up with negative 3 plus 6 minus negative 3/4, so that's plus 3/4, and then minus 3. So that's going to give us a total of 3/4. Right, because the negative 3's together give us negative 6 plus 6 is 0, and so we get 3/4. And so now to find the total area, we just have to add together what we got in both parts. So let's go look back at our previous answer. Oops. So we got 7/12 on the first part, and we have 3/4 here. And so we just want to add those two things together. So the total area is equal to 7/12 plus 3/4, which is equal to, so we can make a common denominator of 12ths, so that would be 7/12 plus, if we multiply this by 3 over 3, that's 9/12. And so that gives us 16/12, which can actually be reduced, right? So 16/12 is the same, if we divide everything by 4, that's the same as 4/3. And so that is our total area, is like 1 1/3. And so, as I mentioned before, I think it's always nice to look back at your area and just like ask yourself if that seems reasonable, and it looks reasonable to me, right? If we look at, an area of 1 would be a box like this, and it seems reasonable that the area here is like just a little bit more than that if you were to distribute it differently. Okay, so we have 2 more examples we're going to do. This next one is going to bring up something that is going to be new for this class, and that is actually going to be really important when we get into the next section about volumes. So this time we're going to find the area of the region bounded by, so x is equal to y squared minus 1, and x is equal to, actually I wrote it this way, so I'm gonna leave it written this way, and we'll see. We're gonna have to change something, but I'll start with it written this way. Okay, so what's different about this? Well, notice that the first equation that we have is x is equal to y squared minus 1. And usually when we're graphing parabolas, they're of the form y is equal to x squared, not x is equal to y squared. So this is actually a sideways parabola. And so this is something that you should have learned about how to graph in your pre-calculus 2 class. So if you feel like you have no idea how to graph things that are written as a function of y instead of a function of x, I'd recommend if you go through my videos, and I'll link the video in the notes for this video. I have a video from 142 that goes into how to graph things that are written in terms of y. But basically all you have to know is that, so if you were to switch x and y, that would give you an upward facing parabola. And basically all you're doing is you're taking that parabola and you're reflecting it over the line y is equal to x. Or another way of thinking about it is that you're switching the x and y coordinates. So maybe just to give you a quick idea, so what would it look like to graph y is equal to x squared minus 1? Well, that would be a parabola like this, right? And so what does it look like to now instead graph x is equal to y squared minus 1? We're basically switching all the x and y coordinates. So this point that was originally at 0, -1 is now going to be at -1, 0. And then these points here, instead of being on the x-axis, are going to be on the y-axis. So the graph is going to look like this. So it's going to have a point here, here, and here. And it's going to look something like this. And actually, I should probably be kind of accurate with graphing it because we want to see the intersection points. So the next point, so one thing that's nice to know about parabolas is this kind of pattern. If it hasn't been vertically stretched at all, you always go over 1, up 1, over 1, up 3. I guess I shouldn't say up in this case because it's sideways, but I guess up 1 over 3, up 1 over 5 is the next one. And then we'd have another point here. And of course, as with any function, you can always just plug in points. So if you wanted to plug in points to this, you would plug in different values for y and see what you'd get for x, and then just plot those points as you normally would. And let me just put in like one more point here, 2 more points. So the next one would be going over 7. So 1, 2, 3, 4, 5, 6, 7. So basically everything you know about graphing a normal parabola, you can just kind of adapt it and just turn it sideways. Sorry, I'm not doing the best job with this. Let me start over. Okay, that part looks fine. Okay. And then y is equal to -x plus 11. Again, I didn't quite leave enough space here, so that's my bad. But one thing that we can figure out from this, so because I cut it off so that we actually can't graph the y-intercept, what we can do is graph the x-intercept. So what is the x-intercept? The x-intercept is what happens when y is equal to 0, right? So when y is equal to 0, if we were to plug in 0 for y, so if we plug in 0 for y, we would get x is equal to 11. So that tells us that the x-intercept is 11. And so we can put that point in here, and then we know it has a slope of -1, so I'll just continue that line. Okay, so this is the region that we're looking at. And let me just shade that in for us. Okay, so what's different about this one? Well, if we were to try to do this the way that we did the other ones, there isn't really a good top and bottom function. And what I mean by that is that if you look at the top and bottom function at this part, so things kind of change here, but if we focus on this part, the top and bottom are actually both the same graph, right? So it just is not quite the same kind of situation as the other ones. So what we're going to do is we're actually going to switch our perspective, and instead of integrating this with respect to x, we're going to integrate it with respect to y. So what we're going to do is, instead of doing the top function minus the bottom function, we're going to do the function on the right minus the function on the left. Because that's kind of, if you turn your head, and that's what you have to really do to kind of switch between x and y, is just turn your head by 90 degrees. You'll see that the function that's on the right would be like the top function, and the function that's on the left would be like the bottom function. And I'll write that out the same way that we did for our kind of normal rule. But let me just label this. So this function here was x is equal to y squared minus 1. And I say the word function, it's not a function of x, but it is a function of y, right? It's not a function of x because it fails the vertical line test. But if you change your perspective and you think of the input variable as being y instead of x, then it is a function. So in order to do this, we're going to be integrating with respect to y. It's going to be exactly the same as integrating with respect to x in terms of the actual procedure. But the one thing that we do need is we need to rewrite this function here. So we need to rewrite this as a function of y instead of as x. And so when I say rewrite something as a function of y, that basically just means solving it for x so that it's like kind of like this one, right? X is equal to y squared minus 1. So if we solve this for x, we would get, so y plus x is equal to 11. And so that means that x is equal to 11 minus y. So this function, now we're going to think of it as x is equal to 11 minus y, or you could call it negative y plus 11, either way. Okay, so how are we going to go about integrating this? Well, basically, we're going to do the same kind of setup that we did with when we did top function minus bottom function, except now we're going to do the function on the right minus the function on the left. So that's going to be the rule that you want to keep in mind with when you're integrating with respect to y. And then our bounds, we're going to start at the bottom bound and go to the top bound. So I'll write that all down in a little bit, but let's see what that will look like for this. So we have the line x is equal to 11 minus y is on top. So that gives us the area where we'll do 11 minus y minus y squared minus 1. So we're doing the right function minus the left function. And then I'm going to say dy instead of dx. And then what are the bounds? Well, our bottom bound is a y value of -4. So you want to make sure that the numbers you're putting in are y values. And the top bound is a y value of 3. So basically, when we go and actually evaluate this integral, one thing I've been trying to emphasize throughout this class is that it really doesn't matter what variable you use, right? Like this integral that we're about to do is the same as if we were to say the integral of 11 minus w squared dw, or 11 minus t squared minus 1 dt. Or we could even replace it with x if we want. That would maybe be a little confusing because x would represent something different than what it represented in our graph. But once you're at the point where you're actually evaluating the integral, it literally doesn't matter at all what variable you're using. The variable here just has significance because it corresponds to our picture. So when we go and actually evaluate this, so maybe let's first simplify this a little bit. So we would have 11 minus y squared plus 1. And so that can be written as -4 to 3. So we have 12 minus y squared. And so if we take the antiderivatives, we get 12y minus y squared over 2 minus y squared over 3. Or sorry, y cubed over 3, my bad. And we're going to be evaluating this at 3 and at -4. So that's going to give us now 12 times 3 is 36. And then we have minus 9 over 2. And then we have minus 27 over 3. And then from that, we're going to subtract, plugging in -4 is going to give us -48. And then we have minus, so -4 squared is 16. And then here, this is going to become positive because when you cube a negative number, it stays negative, and then we have another negative sign. So that will give us 64 over 3. So now we can put these all together. And so we have 36 minus 9 halves minus 9 plus 48 plus, so 16 over 2 is 8 minus 64 over 3. So we can combine these whole numbers together. So 36, so maybe let's look first here. -9 plus 8 is just equal to -1. So that gives us now 35 if we add that with the 36. And then 35 plus 48 is going to give us, so that's, I think, 83. I hope I did that right. 35 plus 48. Yeah, I believe that's 83. And then we have also minus 9 halves minus 64. Oops, I don't know why I wrote 12 there. 64 over 3. So now we can express everything in terms of sixths. So 83 times That's when I have to do in a calculator. So that's 498/6 minus, so this one will be now 27/6. And then 64, we want to multiply that by 2, so that's 128/6. And so altogether we get a total of 368/6. And that can be reduced because both are divisible by 2. So that will give us 184/3. Okay, so let's summarize what happened here. Basically, if your functions, instead of being functions of x, are functions of y, which is what we had here, then you do the right function minus the left function, and you're still evaluating from the smaller bound to the larger bound. So when integrating with respect to y, so the area bounded by f of y and g of y, where, and I'll just say it this way to make it really clear, where f of y is to the right of g of y, from y is equal to a to y is equal to b, and that one I'll just say where a is less than b, so where you're putting whatever the smaller y value is as your lower bound and the larger value as your upper bound. So you just do the same idea. So you do the integral from a to b of, now we would have f of y minus g of y dy. So really the only new challenge that this brings is being able to interpret graphs as functions of y instead of functions of x, which for most of us is not the most natural. And then also just remembering that it's right minus left. Because as we mentioned, the integration process is really the same. So this is something, like I said, that is going to be really important that you get comfortable with, because when we get to volumes in the next video, actually, we are going to be doing some situations where we are still integrating with respect to y. So I want to do one more example in this video. And this is going to be an example where you actually could do it either with respect to x or with respect to y. And I just want to, without actually going through and evaluating the whole integral, I want to set up the integrals for both, just so that you can practice. I think one of the most important skills for when we get to volumes is being able to take something that's written as a function of x and to rewrite it as a function of y. So here we're going to set up two different integrals that equal the area bounded by, so y is equal to x minus 1 squared, and the other function is y is equal to 2x minus 2. So x minus 1 squared, y is equal to x minus 1 squared, that's going to be a parabola that's been shifted to the right by 1. So it's going to look like this. And then y is equal to 2x minus 2, so that's going to be a line with a y-intercept of 2 and a slope of 2. Or sorry, y-intercept of negative 2 and a slope of 2. So it's going to look something like this. And so the area we're talking about is this area here. So I want to do this two ways, one with respect to x and one with respect to y. And again, I'm not going to actually evaluate the integrals. I just want to set them up. but I'd really encourage you to actually try to evaluate them. I'm going to skip it for the sake of kind of length of this video, but I encourage you to evaluate them yourself and see that even though the two integrals are going to look really different, you would actually get the exact same result if you evaluated them. Okay, so what would the integral look like with respect to x? Well, we would be doing the integral from, so we want to look at what is our leftmost point. And so our leftmost point is 1. And then our rightmost point would be 3. So we'd be doing the integral from 1 to 3. And so our top function would be y is equal to 2x minus 2. So we're going to do 2x minus 2 minus, and then the bottom function is x minus 1 squared, which you probably would want to actually multiply out. So another way of writing this would be y is equal to x squared minus 2x plus 1, just to make it a little bit easier to integrate. You could leave it like x minus 1 squared, but then you would want to use a u substitution to actually evaluate the integral. And I think that just makes things honestly a little bit more complicated. So it would be like this. So this would be the top function. Maybe I'll just make a note of that here. So this is our top function, and this is our bottom function. So again, I encourage you to, on your own, evaluate that integral, see what you get as your result. And then what if we wanted to do this with respect to y? So in this case, the two equations were given to us as functions of x, right? So we would need to rewrite them as functions of y. So how do you do that? Basically, it just amounts to solving each equation for x, right? Because right now they're solved for y. And so if you switch it and solve for x, then it will be a function of y. So we want to solve both equations for x. And so the first one is kind of the trickier one. And this is going to be easier to solve actually if we leave it in this form than if we have it in the multiplied out form. So how would you solve this for x? Well, we want to start by taking the square root of both sides. And technically there should be a plus or minus here. But if we look at the picture, the part of the parabola that's actually involved is the positive half, right? It's the part on the right. So if this part of the parabola was involved, we would need to do a negative square root. But because it's this part of the parabola that's involved, we can drop the plus or minus. So I'm just going to say square root of y is equal to x minus 1. And so that means that square root of y plus 1 is equal to x. So that would be how we would write that function as a function of y. And then the other one is y is equal to 2x minus 2. So that one we would add 2 to both sides and then divide both sides by 2. So that would be x is equal to 1/2, or maybe I'll leave it written this way. So 1/2 y plus 1 would be equal to x. So now when we go and integrate this, so we're going to be doing the function on the right. So that's the one that is now written as a square root minus the one on the left. And we're going to be using our bottom value of our bound as the y value on the smaller y value, which is 0. And then the higher y value is 4. And so our integral would look like the integral from 0 to 4. And so our function on the right, again, was the square root. So we would have square root of y plus 1 minus 1/2 y plus 1 dy. And so again, this part, this is the function on the right, and this is the function on the left. So I would encourage you, like I said, to evaluate both these integrals, and you should get the same answer either way, which is kind of cool, right? Because they look really different. Like everything about them is different. The functions are different, the bounds are different, yet they should give you the same area. And, you know, in this case, you might be wondering, like, why would you even do this, right? Like it was just a lot, like just even looking at these functions, this one looks a lot easier to integrate, right, than this one. And plus we had to do this extra work of solving for x. So why would we even bother doing the second way? Well, as we'll see when we get to the next unit, when we work with volumes, there's going to be some situations where you're actually kind of forced to change something that was first presented to you as a function of x. You're going to be forced to change it to a function of y. And so that's the reason I'm bringing this up, is to get you kind of ready for that idea of switching back and forth between viewing something as a function of x and viewing it as a function of y. All right, so that is it for this video, and I will see you all in the next one.